So I guess we're slowly adding people to the class. Some people are taking it jointly with a class that overruns it, a class on zero carbon emissions with Anne Menifee, and so those people will not be here. They'll do it all remotely. As we chatted last time, there are only two things you need to know about this class. One is the resource page, which perhaps you won't use so much, which is this, which has the previous videos on, and the syllabus, but also Canvas, which perhaps is more interesting. And I'll go to Canvas now, just to make the point I did get some questions about how this works. And so the deal is, if you come to class, as you are here, then you do not do the quizzes which are related to the lecture materials. And so those are very specifically identified on Canvas as in lecture 2.1.2, 2.1, etc. So if I bring that up and look at syllabus, then there's a whole bunch of things. I guess two things I did. One, since we're adding people slowly, slightly late, instead of the deliverable for the first ones here being this Thursday at midnight today, I pushed it back to Sunday. And so if you're here and taking the class, I guess you'll do these. But what you won't do is lecture 1.2 quiz, which is the recording of this class from 2022, the last time it was offered. And so all of these ones that start in lecture, you don't need to do. Okay, so you'll realize that if you click on them and see what's there. On each of them, there should be a video, which would be the stuff that's on this course resources page. Some of them are on Canvas or Coursera because they're done during COVID, and that's because we're doing things remotely. The latter ones in the course, I think, are uploaded to YouTube, which is what I do with what I'm going to do with the screen capture today. And if you look at these are the multiple choice questions, not particularly onerous, but just if you're not here, to show that you actually went through the video. Trust but verify, I guess, is the Ronald Reagan era message from that. So that's what we'll do in the class. That's clear? Because I did have some questions about it last time. But the other things that you will do, hopefully before Sunday midnight, are these other quizzes. Some of them are horrible, some of them are great. They're arranged in terms of the topical material, week one, etc. So they're kind of synchronized with the class, even though when the students submitted them, they were their choice, and so they could fall anywhere within the 15 weeks or 14 weeks of the syllabus, but they're arranged in that way. They're not very onerous. They're a bit hokey in some respects, but actually if you want me to have a final exam instead of those, we can do that, but my guess is that perhaps you might not want that. I'm not sure. Perhaps you might do. I always thought exams were good as an undergraduate student. You kind of had to bite the bitter pill, but it means you could slough off during the semester and do your own thing. So, okay, that's our plan for the class. So, everyone good? Fine. Everyone with their laptop screens up watching cats fighting on YouTube? No response. No, not you. I'm looking over here. Fine. No. Yeah, fine. So this is by way of just, I'm not sure whether to stand up or not. If I stand up and walk around, I kind of like doing that, but I don't have a mic and it's recorded through this. And so what I wanted to do today is just a big picture view of energy and how what we're talking about in terms of geothermal energy fits into that, energy globally. And so we'll talk about renewables and how that fits into the global energy outlook, power supply if you like. this is the change title. It's the same as the ones in your notes. So you'll notice also that if you look in your, if you download the course notes, which would be these, and yeah, fine. So you'll see that within the course notes, we looked at this the other day, albeit on the screen with the PC. This is the compendium that has the syllabus in that we talked about, the scheduling, the deliverables for the presentation, your presentation. We didn't talk about this. This is just something that I pulled out of a, I can't remember where I got it now, but I think it's kind of interesting. It looks at the rough sizes of some items, both in terms of SI notation, in terms of kilo, mega, giga, tera, in terms of the uses of powers of 10 to the 3, multiples of 10 to the 3, and 10 to the minus 3. So if you're unsure of that. It also looks at the terms of general sizes of some of these resources on the planet. And as we go through this presentation today, we'll find out that the total energy use in 1 year on the planet is something like 500 exajoules. Exajoules is a joule times 10 to the 18. Hopefully, it's up here. Exa, right here. And the US uses something like 20% of that, with maybe 5% of the global population. So maybe we're a bit greedier, or maybe we're more energy intensive than other places. So you have some idea of those. It talks about solar radiation, the energy that's expended in an earthquake. I always think that the energy that's expended in an earthquake, a magnitude earthquake, in a year, 500 exajoules, which is the energy that's expended in a year for the power, the rate of doing work per unit time for the planet, is roughly the same as a magnitude 8 earthquake, which occurs once every year, roughly. And a magnitude 8 earthquake is done in about, like any earthquake, is done in about 90 seconds as opposed to a year. So quite powerful items. Talks about different quantities, so I think it's just an interesting reference. And these two figures are kind of interesting in that they talk about power per unit area. Yeah.
I don't think we're seeing it right here. Shall I say that?
Thank you. Okay. No. That's good to know. Okay, I can do that by doing this. Good. Should have talked to her. Yeah, shall. Did you try and catch my attention, but I wasn't looking? No, that's okay. That exonerates me then. So I'll go back through this. So this is this compendium that you have. So you have this. If I were you, I would download it, because I will work from this in our classes. So these are the multiples of 10 to the 3, which are kilo, mega, giga, tera, peta, and exajoules, etc. And the 10 to the minus 3 for centi, milli, nano, etc. Pico. Some rough ideas of some global magnitudes of things, like energy that's available. We make the distinction between energy, which is joules, if we work in SI, and power, which is joules per second, which are watts here. And so we need to make that distinction. Talk about different forms of energy coming naturally, and I guess in this, energy flows and powers. So energy is in joules, power is in joules per second, which is a watt, W-A-T-T, after the steam engine watt, the guy. Yeah. And I guess the last thing I was going to mention, talk about the amount of energy locked up in different compounds, conversion efficiencies, I guess, that's important, right? If you're putting a certain amount of electricity into an electric motor, but it's only got a certain efficiency, then you can work out how much you get out of this with the loss that's in the system. So that's kind of useful. I'm not sure that we'll use them in this class. Energy costs, megajoules per kilogram. That sounds like energy density to me, I would say. And so things like, or perhaps that's energy cost in refining, making aluminum out of bauxite, I guess. So I guess that is per kilogram. How much energy you get out of conversion of a kilogram of some component. And I guess these are both interesting components. One is in terms of power per unit area. So this is a power density for different things such as a house. So they're all constrained by these straight lines, which are watts per square meter, large numbers, which are large high energy densities, and small numbers, which are small power densities. I guess it's not energy densities, it's power densities. And the rough magnitudes of things that take up different areas. So I think that's an interesting thing to talk about. So now we're on the same page. So I will get rid of this. So it just didn't swap. So what I wanted to chat about, good. So in terms of the big picture of energy. So this was put together both for this class, but also for a class that we used to specifically take to New Zealand as a 497 class, a general class. We did it in 2017, 18, 19. We were scheduled to go in 2020 on the Tuesday before we were scheduled to leave. On the Friday, just before spring break, the course was cancelled because COVID, and everyone was sent home, so it didn't happen that year. But it was resurrected again, and we did it in 2019. And so New Zealand's an interesting place to go to because it's maybe like, along with Iceland, one of the few places worldwide that is blessed with a renewable resource just by virtue of its location. It sits almost on astride a plate boundary, as does Iceland in the North Atlantic. It straddles the European and North American plates in the case of Iceland, and this straddles the Pacific and Australian plates in the South Pacific. And so it's an interesting place to go to be able to view geothermal energy at work. And perhaps we'll look at some pictures a little later. These are a couple of interesting quotes from Richard Smalley. Richard Smalley is a Nobel laureate who's credited with buckyball, carbon-60, in the shape of a soccer ball. And both he and John Holdren was Obama's science advisor a few years ago now, that making the case that this nexus between energy and environment is incredibly important. We live on a planet where we need energy. Industrial societies require energy and are productive as a result of it, but you perhaps don't want to destroy your environment because that's what you live in. And so it's a balance between the two of those, because environmental protection perhaps costs more than not environmental protection. So the balance between these three is kind of an interesting thing to behold. I haven't updated this for a while. This is probably from it probably stops in 2013. This is my recording of a website which is called the Gapminder. You can see the web address in the bottom right, which was produced by a guy called Hans Rosling, who's a medical doctor, a physician who worked in Africa but was Swedish, and when he returned to Sweden thought that providing statistics in a way that people could digest was an interesting activity for him. And he's the kind of guy who's done lots of TED Talks espousing the idea that statistics can tell you, if they're plotted correctly and usefully, can tell you a lot about systems. So I remember he made the case that how the washing machine liberated women, because all of a sudden the fact that you could do that work when women worked in the household and not else, that you could actually take care of the time that it would normally take to do washing, do it quickly, and allow time to spend on other things, going out of the house to work, for instance. And so this is one of his plots that plots on the base income per person. So this is GDP divided by the number of people living in a country, salaries if you like. And it's the vertical axis takes two forms. The first form is in the previous one is in energy use per capita. And so you see this slope up to the top right. High energy use relates to high income. And you see over time, if I go back, that as time goes on, you see different countries, population in the diameter of the country, continent given by the color, and the location of that chart says how energy intensive those environments are. And you see that the richest countries, if you take GDP per capita as a measure of that, are those that have the highest energy usage, energy density per capita. The second figure, the vertical axis, changes from energy use per capita to CO2 output per capita. And you see in that case it roughly mirrors the same things. It doesn't matter about the units, but it's always a slope up to the top right hand side. The most industrialized nations end up being furthest to the right. The data are slightly longer than this. You see the years ticking away. First World War now, interwar period, Second World War, etc., going on till to present. And you see that the basic idea is that industrial societies are energy intensive and have the highest incomes, and maybe if you take that as an indicator of happiness, as opposed to gross domestic happiness as Bhutan uses as a measure of how well you're doing, then energy is an important part of what we use. Unusual when a president leaves office, as Obama did in 2016, to have a science article, Science and Nature, maybe the top scientific publication, most prestigious scientific publications, but only for general readership. Each of those publications, although maybe if you listen to NPR, they'll talk about a study that came out in Science or Nature, they're actually built for the lay scientist. So they have stuff from biophysics, astrophysics, geosciences, engineering, biosciences, medicine, but they're all supposed to be articles that a lay person can understand. And so it's not an unusual place for him to present this. And he was touting the contributions of his administration in the 8 years that they were in power. And so they're noting the fact that greenhouse gases dropped during that by some significant amount on 4 occasions. Often it's associated with a drop in output, in other words, a recession, but at least the last time it dropped in his administration, it wasn't. And perhaps you could credit that to the fact that natural gas was replacing coal, so it's still fueled by greenhouse gases, greenhouse gas generating fuels, but it wasn't all renewables. Electricity from gas changed from 21% to 33%. Presumably that change by 12 basis points was at the detriment of coal, which would have been switched to go to gas. Employment in renewable jobs increased, and energy usage was reduced by making society more efficient. So one way to look at energy flows in a nation or worldwide is to use what's called a Sankey chart. This is equivalent of this. I have this on on our wall in our house. It's Napoleon's march to Moscow. Setting out is in brown. The width of the band is related to the size of the army. Get to Moscow. The losses, I think, are due to bad weather, as it was in the wintertime. Tchaikovsky's 1812 symphony was written about this, commemorated this. And, whoops. And the return journey is in the black, and on the bottom you have the temperatures being plotted as a function of time. And so this is some form of Sankey chart. You can look at energy flows on the same diagram. This happens to be one for the US. It's compiled every year by Lawrence Livermore National Lab. This is from a few years ago, 4 I guess now. And it talks about the energy flow from initiation to usage, consumption or usage at the other end. And so in the US, as I mentioned, we use something like 100 exajoules per year. That would be, if you used only natural gas, that would be 100 trillion cubic feet of natural gas, or 100 quadrillion BTU. They're all roughly the same in units, which is kind of interesting. The world uses something like 500 exajoules in a year. And so, as I mentioned before, the US uses maybe 20% of the total usage in the world, 300 million population out of 6 billion. We're probably 8 billion now. But that would be 300 out of 6 would be 5%. So we're slightly less than 5%. And this 100% usage would relate to the right-hand side, the left-hand side of this chart. Does this come up on this? Yeah. So these all sum, they're a bit small, but they sum roughly to 100. The fossil fuels here are the ones from natural gas and petroleum on downwards. The renewables are the ones above this. The rough thicknesses of these blocks in terms of these lines are actually the percentages. So you see geothermal on there is relatively small. My eyes aren't good enough to read it, but I can on this one. Geothermal is 0.206 of the output. 0.2% because this is roughly 100 quads or 100 exajoules on the left-hand side. And the overlays on this particular plot are due to the energy policy that was enacted, I guess, in 2008 by Pat Deemer, who was chair. She was chair of the Office of Science, in defining the strategy to go to a transitional economy. And the idea is basically this. If you look at the energy flows, this is the end use of these. And so as you go from using a large portion of fossil fuels, probably 70% of the usage in this time, it hasn't really changed very much. If you look at a more recent one, say from 2024, I didn't put that plot in, but it's changed. Maybe solar has doubled in terms of its actual utilization, but that's only made a change of 1% in this. And maybe wind has also doubled within that period of 2 years, but it's only made a change of about 3% overall in this picture. The big changes have been that coal has reduced at the expense of natural gas. It's already changed a lot from the previous 5 years at this time. And so that fuel switching is one reason that greenhouse gases have been reduced. And if you know what these energy flows are through the system from recovery and processing, utilization at the right-hand side, then you can make a strategy. So the observation that more than 50% of the power is rejected energy is if you could use the heat that come out of industrial systems somehow for district heating, that would be quite a good use because you'd be able to substitute some raw primary power or energy that was used for that with some waste product that just gets ejected to the atmosphere. The actual usage of power that you generate is only something, is it 30%? It's 31%. So if you can use more of the stuff that you activate, then you'd initially reduce your power consumption perhaps. You can fuel switch to use lower carbon natural gas instead of coal and reduce the carbon output. You can burn fossil fuels as usual but sequester it underground as an option. You can fuel switch from heavy carbon fuels to lower carbon fuels, petroleum or coal to natural gas. And you can also allow renewables to penetrate the marketplace as well. So these are the rational ways that you can think about doing that. And the other things that you have to worry about is having a electricity distribution and energy storage for these renewables, because when the sun shines, you make electricity, you have to store it sometime. You can't just not generate it, and you have to use that. Yes, sir. Can you shout? Outdoor voice? Rejected energy. It's the stuff you don't energy. When you drive a car, You use a certain amount of gasoline. Gasoline burns and it drives the car. The energy you've used is the power you've taken to get you in the car from A to B. But the heat that's in the car is just rejected to the environment. So it's mainly heat from that. And some noise as well. Yes. Yeah, thanks. So global carbon cycle, I think this is interesting. Not going to dwell on this, but the idea is that there are huge carbon fluxes in the environment. Some are natural and some are artificial. The natural ones are largely in balance in that the sinks and sources of carbon roughly balance each other. The only mismatch, so you see huge sinks and sources between atmosphere and water of 70, these are in petajoules of carbon. So petajoules must be a gigajoules, petagrams. So these, well, I know that these are gigatons. So this is 5 gigatons of carbon. So these would be 70 billion tons of carbon that is exchanged between the atmosphere and water. But the only thing that we're changing the system by is we're changing it by something like 5 to 7 gigatons of production of carbon per year, which comes from typical fossil fuel burning. The operation of the greenhouse effect is pretty well understood. We need it on this planet. We sit a certain distance away from the sun, and we have an atmosphere. Closer to the sun, you burn up like you would do on Mercury. Further away, you'd freeze like you would on Mars. Close enough, we have some solar insulation. If you didn't have an atmosphere around us, that solar insulation would perhaps bake us. If you look at the moon, which doesn't rotate as it goes around the Earth, it's always facing the sun or not facing the sun. The temperature contrast from one side to the other is something like plus 60 to minus 60 as you go across it. So we would have that if we didn't rotate, and if we didn't also have an atmosphere which traps in some of the infrared radiation from the sun and allows us to store it in the atmosphere. A certain amount is good because that's how we survive under the current conditions. Too much carbon traps in more temperature, more heat, and therefore the temperatures go up. It seems kind of unequivocal that that's happening. We know how the greenhouse gas effect works, but the interpretation of that as to whether climate change is a hoax or not is based perhaps on understanding what the costs are to deal with that. And of course, that is an activity full of debate. And so if you look at how the science has been defined and has been set for 20 or 30 or 40 years, we've understood this process, but certainly the approaches to dealing with climate change and society's choice of how to deal with it has certainly changed through the years. As you go through these, just merely to cycle that depending on what administrations have thought about the cost of dealing with these things as to whether it's worth it or not has largely dictated what policy would be. And so we know what the differences are between policies on different administrations. But to mitigate these things, all things being equal and not being worried about the cost so much, then the kinds of things that were put in place during the Obama administration were to be able to conserve, drive more efficient cars, drive up the CAFE standards to get larger mileage from existing cars, switch to EVs or hybrids, and increase the penetration, if you like, of renewables into the marketplace. And to do this with cap and trade, which hasn't turned out to be particularly successful. It's a net cost and a drag on economies. It's been applied in some places and still is in place, I think, in Europe and in Canada, but sometimes with mixed results. So a lot of these things, actually, apart from building more wind turbines and having more thermal energy, PV and solar energy, relate to the subsurface. So many of these things relate to the subsurface. Switching natural gas for coal is a subsurface engineering problem. More geothermal is a subsurface engineering problem. More nuclear, you need to dispose of the waste. Well, you need to mine the uranium from the subsurface, and you need to dispose of the waste typically in the subsurface. And so many of these things relate to the subsurface, which is really what the essence of this course is. but related primarily to geothermal. The other way to look at this process is to this paper by Pakala and Sokolow, a couple of guys from Princeton University. 2004 is the original time of this paper. And at that time, if you look at the rate of production of greenhouse gases, we just looked now, the production of carbon was 5.4 gigatons per year. Here it's 7, so it's actually 5.4, I think, on this. But that's gigatons of carbon a year. So CO2 would be from the stoichiometry. You have to allow for the oxygen, the two oxygens that's on CO2. So it's something like 40 gigatons of CO2 per year. Business as usual, and the utilization of fossil fuels on the globe continues to grow, you'd expect to go on this path here. If you want to stop now and flatten out the carbon usage, then you have to stop using fossil fuels, and to be able to do that, you'd end up going a trajectory which is this lower trajectory. So if you want to do that, you have to replace the carbon that would be represented by this wedge, 50 years wide by 7 gigatons per year tall. So you could work out that would be 50 times 3.5, all right? Half base times height. So 50 times 3.5 would be 175 gigatons of carbon avoided if you got rid of that green wedge. And what their paper was making the case for is that to make that kind of accommodatable and real to people, is a paper in Science, this layperson's science magazine, would be to divide it up into these 7 stabilization wedges. So each of these wedges represents, by the time you're 50 years down the road, 1 gigaton of carbon avoided in the 50th year, and slowly ramping up to that over that time. So it'd be 50 years times 1 gigaton of carbon avoided. So it'd be 25 gigatons of carbon avoided over the full length of these stabilization wedges. And to make it meaningful to people, figure out exactly what these stabilization wedges meant in something tangible. And so each one of these slithers would represent, doing relevant to this class, replacing 80 large thermal coal-burning power plants by an equivalent amount of power from geothermal energy. You could do it by geothermal. You could do it by pumping the CO2 from thermal plants underground for those 800 power plants. You could do it through nuclear power, building 800 nuclear power stations that are 1 gigawatt each, a typical size for a nuclear reactor. You could do it by switching coal for natural gas, but because natural gas still has half of the carbon of coal, you have to replace double the number of coal-burning plants. Or you could do it by driving more efficient cars. And so you can think of it that way. So that's just to do one of those single slithers that ends up as 1 gigaton of carbon avoided after many years. So many of those solutions relate to the subsurface. Nuclear power, big problem, dispose of the waste. Geothermal, get the heat out of the ground. Carbon sequestration, inject the fluid, make sure it stays there for a century, centuries. And so increase natural gas production, make sure you can do that in large sources. And the most abundant sources these days are in gas shales, which are also a challenge to be able to develop. So very quickly, maybe just run through some of these subsurface solutions just to give you a feel for what we're talking about in geothermal energy from the subsurface fits in, because a lot of the techniques that are used for these other things are common to that area. In fact, the big growth now in deep geothermal recovery of energy is being spurred by techniques that have been developed over the last 20 years probably in the so-called shale gas revolution, where the recovery of gas has been unlocked from relatively super low permeability shales, which if you drill a hole and pump them, nothing comes out. And of course the technique of massive hydraulic fracturing has been what's driven that. So we'll talk about low carbon fuel solutions would be replacing high carbon coal and petroleum with natural gas, which has less carbon per unit energy recovered. Carbon management would be business as usual, but put all the flue gases underground. And zero carbon solutions, we'll talk about geothermal and nuclear. Won't really talk about hydropower or wind or solar. It's kind of beyond the scope of this class. Very quickly, low carbon fuel solutions, gas shale. Big thing in Pennsylvania. Arguably, you could make the case that it carried the economy through COVID, just from the recovery of natural gas, and has boosted Pennsylvania's economy. It was hailed as the rock that could power the world. George Mitchell, in around the early 2005 or so, unlocked the idea. Finally, after trying many times to recover shales from low permeability, recover gas from low permeability shales, hit on two important things. One was horizontal drilling. You drill down and then you go 90 degrees and spend 2 or 3 kilometers inside the thin shale bed, so you have a lot of waterfront in that shale, and also hydraulic fracturing, massive hydraulic fracturing. So those are techniques that were developed to recover shales. Gas shales are ubiquitous. They exist in many places, certainly in North America. They exist in Europe, in Poland, in Eastern Europe. They exist in Argentina. They exist in China. They exist in Australia also. In different places, they happen to be of different quality. It happens that the ones in the US are actually quite high quality. Quite high quality means that they've got lots of organic material in them, high total organic carbon contents. They've been buried deep enough but not too deep that they've been cooked to be able to process that organic content into methane. And they have low enough permeabilities that they've trapped that methane inside the rocks themselves rather than allowing it to migrate into a cap, which is what a conventional petroleum reservoir is. The fluids are lighter than water. They get caught in an impermeable cap, which holds them, and then you drill into the material below that cap, and you recover those directly out of this surrogate formation that they've migrated to. In gas shales, they exist within the shale themselves, and you have to work out ways of putting them. The other good thing about Pennsylvania and US shales is that they're also brittle, so that when you try and prise them open by injecting fluids, they break very easily and they break very brittly, and they create lots of permeability. If you look at the Chinese shales, for instance, you find out that they're not so brittle, and the gas contents tend to be much lower because of lower organic contents, and the permeabilities are slightly higher, that over geological time the gas content has escaped, and therefore they're not quite so lucrative. So North America happens to have the highest quality shales. So the ideas are shown on this figure. Vertical well that goes down has a kickoff point where you put a wedge in the well that diverts the well slowly around a radius to go horizontally. In Pennsylvania, these shales are at 9,000 feet deep, 3,000 meters, and these wells can go for a few kilometers in length. And then once you create these wells, you case them, you cement them in behind them. So it's a sealed conduit that the gas will ultimately go into and be carried in this pipe, this steel pipe up to the surface, so it doesn't interact with the groundwater that goes across or with other places in the reservoir. And then once you have this pipe in place, you put a perforation gun which fires shaped charges through the casing, and then allows you to pump fluids into it to hydraulically fracture it. And then these fractures are what makes the porosity and permeability with a large surface area that allows you to recover the gas out of it. So a technique that was developed by trial and error, but now is incredibly technologically advanced, not without its environmental detractors, but it comes with some environmental cost. The other form of natural gas is in coal beds, much smaller reserve than shale gas, maybe by an order of magnitude. The U.S. has deposits, as are shown there, San Juan Basin in the Appalachian and in the southern part of the U.S., in Alabama, etc. Same ideas. You have to be able to drill into them, create permeability, recover the gas, and use that to be able to substitute for things like coal, leaving the coal in place and just recovering the natural gas from it. The other really large natural gas, again, natural gas from shales, natural gas from coal bed methane, and natural gas from hydrates are all fossil fuels. They're all methane. But hydrates are naturally occurring gases that result when rivers bring down high organic content in the bed load that they take from erosion upstream and dump in a delta offshore, just like New Orleans is a delta. The organic material is buried in the subsurface. As more material comes down, it gets buried further and further. And as it gets buried further and further, as we'll talk about for geothermal energy, we talked last time about the geothermal gradient being 25 degrees centigrade per kilometer. It gets cooked as it gets buried deeper. As it gets cooked, the natural gas off-gases and rises buoyantly in the column. If you look at the temperature of water at the seabed, which never gets less than 4 degrees centigrade, that's when water is most dense, and so the temperature of the seabed will be 4 degrees centigrade. There's a thermodynamic trap that will catch the methane gas as it comes up, combine it with water within the sediments, and lock that gas into a cage within the water as a hydrate. Definition of a hydrate is just a molecule of natural gas that is placed within a cage of frozen water, and it exists as ice. You get it blocking pipelines if the temperature regime is correct for that. You also get it offshore in these layers which are below the seabed and kept in this thermodynamic trap which results from the competition between the geothermal gradient pumping heat up and the steady temperature of the water at the base of the water column. And it creates these frozen materials that you can burn. It can burn because it has a methane molecule locked within a water molecule in a kind of cage. And so if you can recover this, it's turned out to be a very difficult problem because they are very low permeability, same problems as shales. You can melt them, but if you melt them by injecting hot water to recover the methane, they tend to just melt and go to mush. And so the problem of recovering those still isn't solved. It's the only reserve I know that with time has gone down. Often you explore for natural gas, you find a field, and your reserve is this big. You find another field, and all of a sudden your reserve is double that, or 1.5 times that. Hydrates have gone the other way. The initial estimations were in taking every location around continents worldwide, saying that this is a thermodynamic trap. We think we have enough organic material to create a lot of natural gas. We know the height of this thermodynamic trap, so let's assume that all of the sediments in this zone are filled with hydrates, and then if we do that, we can calculate this volume worldwide, and therefore we can calculate exactly what the method is. It's turned out after the fact that the saturations of these, the amount of hydrate within the sediments is actually much lower than that maximum amount you could expect. But it's still a huge reserve. It's probably the largest natural gas reserve on the planet. So if you can unlock it, you make yourself a rich person. And so the idea that you could replace coal burning with burning natural gas and still off-gas the flue gases means that you have to replace 1,600 very large power stations as gas-fired. And of course, if you travel around Pennsylvania, now if you want to build a power plant, you don't build a coal plant, you build a natural gas one, because you just take an engine off a 747, and that's what a natural gas turbine is. Yes?
So with the methane plate grids, they would obviously have a water or H2O molecule connected to the grid. So is the energy coming from it weaker and being marketed in natural gas?
If you wanted to recover energy from it by melting the ice to get the methane out, you'd have to either provide energy for doing that, or what you could also do, you could drill a geothermal well in exactly the same place and use natural waters from below it to be able to melt it. So if you want to liberate it, you've got to either three ways. You can either melt the ice by providing hot water, heat, usually with the fluid, hot water. You can lower the pressure, and it melts as you lower the pressure. Or you can provide what they would call an inhibitor, add salt, just like melting ice on your driveway. So an abundant resource, but a difficult one to deal with. You could also burn coal as usual and put the flue gases underground. Typically you wouldn't put it as a gas, you'd compress it to be larger densities, so you have to pump less volume, but it costs to be able to compress it. And if you do that, you want to be able to inject it into some places where you think it won't escape from. Good places for that would be depleted natural gas and oil fields, because those have been sealed already over geologic time, so long as there aren't lots of drill holes that allow access to the surface. You could put it in coal seams as you take out methane. You could pump in the CO2, and pumping in CO2 into coal displaces preferentially methane, and it off-gases methane, which you can then recover as a method of enhanced coal bed methane. Or you could put it into saline aquifers, where there's water which you'll never use because it's salty water, it's not potable, and use those to be able to store it underground. And so that is fine. Most of these places probably have the capability to contain it over the kind of geological time we're talking about. But they're expensive to be able to do that. And to do that, you've got to replace 800 coal-burning power plants, as we mentioned. Geothermal energy, that's what we were talking about. Someone asked last time about exactly how that worked. Well, there are a number of systems that can be done. Most of the current capacity of this 0.2 of a quad in the US that we saw in the previous figure comes from what's called hydrothermal deposits. Those are the ones that have high permeability and high porosity and are shallow, hot at shallow depths. There are places like on the west coast at the geysers, just north of San Francisco, where you have hot springs all over the place. You just drill into them. There's enough deformation going on at the plate boundaries that you can recover the fluids, the naturally heated fluids, very easily. The holy grail of geothermal energy is so-called enhanced geothermal systems, where under New York City, where there is no such geothermal heat close to the surface, you can drill down 3 kilometers, 4 kilometers, where the heat is going to be 25 plus 25 plus 25 plus 25, maybe 110 or 130 degrees centigrade. So the heat de facto is there, but the only way you can get it out of it is if you have some heat transfer fluid to circulate between them. So you drill a well bore, you try and create permeability in the subsurface, as shown in this little cartoon. You drill another borehole somewhere away from it, perhaps 500 meters away, perhaps 5 kilometers away from it. And from that material, you try and inject the cold water, the blue borehole, to the red boreholes and recover it up to the surface. And by that means, recover the heat from the subsurface. It's not quite as easy as it says. It's been something that's attempted for 50 years, and there isn't to the date an operating geothermal system that does that. We may be pretty close to it now, but we're not quite there. And this shows 2 things, I guess. One is the the high-grade heat map for the US. It's pretty cold in the northeast. It's a bit warmer on the western borehole show. Volcanic, these would be the places where we have both permeability and high heat flow at shallow depths. This is hot, dry rocks where we have to make the reservoir to be able to do this. And so this one is the main challenge. This is the one we know absolutely how to do, but most of those resources, the low-hanging fruit, are already in production, and there's access to no more in the system. So if we do anything in geothermal, for deep geothermal, it's either sedimentary aquifers, which we can use, which are usually mid-heat, maybe 100 degrees centigrade, rarely much more than that, which would be useful for district heating. Can also generate electricity from that, as we'll find out. Or high-grade deposits by going much deeper and doing it close to the markets. You use it in New York City, so you'd like to be able to produce it at the same location. If you want to make these viable, you have to, because of the high cost of drilling a well, a 4-kilometer deep well perhaps costs $10 million. And so the cost of putting 2 wells down to be able to recover fluid means that the payback over 20 or 30 years is you have to have a certain amount of output, energy output, to be able to do that. And the break-even point for that is something like 5 megawatts per well, and that accounts to something like 100 kilograms per second at 100 or 200 degrees centigrade, integrated over the 20 or 30 year lifetime of a project. And so these are some historic EGS systems, are the bars. Fenton Hill was the first one at Los Alamos National Lab in 1974. There are some other ones on after the 2010s on this. This is in New Mexico, this is in the UK, these are in Japan, this is in the Rhine-Graben between France and Germany, like this. Desert Peak is Nevada, Coso is Oregon, Newbury Mount, Coso is California. Salts again is on the Graben between France and Germany, and Cooper Basin is in Australia. So the issue has been in terms of doing that. I'm not going to get through the other ones, but I don't worry so much about them. Let's see if this works. Is this going to work? Yeah, it is. It's a bit of a public...
No competing solution does this. Coal and natural gas are not green. Wind and solar are not available on demand. And hydro and geothermal are not truly scalable. To move beyond partial intermittent solutions, we need more than wind, solar, and batteries. We need
Loop. Ever fills this need by taking a niche energy source, geothermal, and finally makes it scalable by eliminating the need for volcanic temperatures or permeable aquifers. Ever does this by leveraging advances from North America's shale drilling revolution to mine heat directly at scale via conduction rather than by producing out fluid from an aquifer. Ever mines this heat by creating what is essentially a radiator kilometers below the surface, composed of the effective equivalent of up to 100 kilometers of hermetically sealed wellbore. Our IP is how to implement, operate, and configure this radiator in a safe, scalable, and
For me, the jury is still out on whether this can work or not. It's a little different from the things you talked about. The idea is you drill down and you can get these boreholes to meet. You case them so it's a closed system, and you do this. The problem is that because you have so little contact with the hot reservoir, the heat transfer area across this pipe is really quite small. And so I'm still not sure whether this works. So I know there's one in Rocky Mountain House, which is between Calgary and Edmonton near the Canadian Rockies. That was maybe the first one. There's some of these in Europe. They're very far distance apart. The separation on the surface is 5 kilometers. If you look at this, it's not marked. And so the technology can do this. So you can do this. These laterals are all done and joined so you can pump from between them. If you have two wells at one place, you don't have to have a connecting circuit along the top, but you can pump up through one and then pump down cold in the other one, as you showed here. The blue would be the injection of cold fluid, picking up heat as it goes across to the other side and coming up hot. You take the heat out of it, make it cold again, and go it down. They use a proprietary fluid. It might be CO2.
Netherlands, and combined heat and power.
It might be CO2, because when you heat CO2, it becomes really much less dense and therefore buoyant. And so rather than having to pump it up, it rises on its own, the so-called heat pipe effect. And so it's a very clever technology. But what I can't work out is how they get the heat into the very small heat transfer area that's here. So I'll leave it at that. So this is a variant, if you like, on the idea of using geothermal energy. And I'm not going to get through this whole thing, and I don't want to, particularly. But this is. Oh, you do see that. I guess. Yeah. So just to round things out. So if you want to replace retired coal-fired plants with EGS, you need to replace 800 gigawatts of it. A big, tall order now, since we don't have that much available. So the current capacity in the U.S., the Geysers, is about a gigawatt geothermal field, just north of San Francisco. I don't know what the total capacity of the U.S. is, but it might be a factor of 2 or 3 times that. So we may get three large thermal power stations worth of geothermal energy in the U.S. The other one is to switch to lots of nuclear reactors. It's kind of happening now in the U.S., certainly happening in China. With the new administration, that's a more favorable solution than it was before. And then the problem becomes nuclear waste disposal, and I suppose actually getting uranium. Getting uranium is not easy, because I think the U.S. probably still buys uranium from Russia, despite the Ukraine situation. So the big challenge for nuclear waste is what to do with it. We did have a planned repository at Yucca Mountain. Obama had a blue ribbon panel discuss whether that would go ahead, to decide that it wouldn't go ahead in about 2009. The thought was that panel was to appease the then majority leader, who was the senator for Nevada, in which this would be, who didn't want spent nuclear fuel being transported across his state, and that as a result of being relieved of that, would actually vote on the American Health Care Act, Obamacare, to get it through Congress. So some seedy and strange dealings. So again, for radioactive waste, a big deal is what to do with the waste. There are some plans, and I'm going to leave it there. And so just to come back to where we were, there are lots of solutions to our energy problem, if we deem it a problem, in reducing the amount of carbon. We've talked in a big picture style about how we can do them. It's interesting that a lot of them, even though we're only going to talk about geothermal in this class, a lot of them are related to the subsurface, which we have to understand. And geothermal also has been advanced in the last 5 years in a big way by adopting the characteristics of shale gas revolution. The two things that made shale gas happen was that you can drill very quickly and cheaply into the subsurface, and for long distances horizontally, to have a big contact with your reservoir. And a big contact could mean easy transit of gas from the shales or heat from a hot reservoir into the borehole, and hydraulic fracturing to be able to get the fluids to come that bear either the gas themselves or water that's brought into the well that carries heat with it, to take the water up to the surface, remove the heat from the water, and re-inject it. And so many of the things that we'll talk about have commonality with things in the petroleum, oil and gas industry. Some are specific to geothermal, but all of them are related to the subsurface. Even for things like CAES, so energy storage, pumped hydro, taking water from a lake at this level to a lake at this level. You pump when energy is cheap at night, and you let it come down when energy is needed in the daytime. Compressed air energy storage, is pumping compressed air into the ground when energy is cheap at night, and then releasing it back through the wellbore and through a turbine in the daytime when you need it, again using the subsurface, and wind and solar, which aren't so relevant to the subsurface part, but actually in terms of storage of energy for both wind and solar, the subsurface is often used. For solar and wind, you can create hydrogen from water, which you have to store somewhere. If you want to have grid scale access to that, you can't put it on tanks on the surface, you have to store it underground. Either underground in salt caverns, which is an intermediate volume, or pump it into porous reservoirs, which is a grid scale solution for that. So all of these things are related to what we'll do underground. We took some students to New Zealand, which is what this course is about, and that's going to be my last slide. So that sets the picture. So everything that we do in this class from now on will be talking about how we mobilize to be able to get geothermal energy out of the ground. My great love is deep geothermal, EGS, and hydrothermal, where you have to drill down a couple of kilometers. But the most sustained and perhaps most impactful part of geothermal is in things like ground-sourced heat pumps. So on February the 22nd in 2022, when all of a sudden Europe decided that it didn't want to get its gas in the Nord Stream pipeline from Russia, then one of the solutions to that was to use heat pumps. And the most efficient heat pumps are to use ground-sourced heat pumps that take the relatively low quality geothermal energy that's present maybe at 3 meters depth with a large array to be able to suck that out and use that to supplement the phase change behavior of a big air conditioner. And so we'll also talk about that. So I will leave it at that. All of you are exonerated from doing the online quizzes. So I have a sign-up sheet here. I hate to redress to that. I don't know if I can figure it out for you. These are you. Do you want me to take a go at doing this here, or do you want me to just hand it out to you? Come on, talk to me, talk to me. I can hand it out to you. I've had enough trauma today trying to get the audiovisual working.